Hey guys, so today let's talk about something called the VSEPR theory. VSEPR is nothing too hard. It just means valence shell electron pair repulsion theory. Now I know it sounds hard at first, but once you get it, it's actually pretty simple. The theory simply states just two things. The first one is that electron pairs repel each other, so they can be as far apart as possible, which is reasonable since all electrons have a negative charge. And since like charges repel, they want to be as far away as possible, but without breaking the bond, that is. And there are two major types of electron pairs, so-called bonding pairs and non-bonding pairs. Let me show you on a real molecule. So here, for ammonia here, we have three bonding pairs, right? Three pairs where the nitrogen bonds to the hydrogen. And these two electrons, which is a pair that doesn't do any bonding. So that would be a non-bonding pair. The space taken up by a bonding pair is called the bonding domain. And of course, the space taken up by a non-bonding pair would be called the non-bonding domain. Because VSEPR states that electrons want to be as far away as possible, this also affects molecular geometry, in other words, how molecules are shaped. Here I have a few basic geometric structures in 3D. Now you may see that AX is trivial. It's that sometimes some people say that it's kind of trivial, so I noted it, but I just added to the chart just for completion. So here's also the basic shape of the molecules. As you can see, the angles are all structured so that all of the atoms can be as far away from each other as possible, since, well, bonding domains don't like to be around each other. So as you can see, these angles are the closest distances between an atom and another atom. Also, some molecules have multiple angles. For instance, AX5 structure has a 90-degree angle and a 120-degree angle. The 90-degree angle is from the top atom and the side atoms around the equator of the central atom. And the 120 degrees is from the top view. Between the equatorial atoms, there's a 120-degree distance because a full circle is logically 360, and because of that, the distance between the three atoms to maximize the distance would be, well, 120 degrees. But wait, we can't just have those simple structures like AX and AX2. We also have these fellows named the derived structure. The derived structure includes the non-bonding pairs of the standard pair. So let's say we look at AX4. The AX4 structure doesn't have any non-bonding pairs. If you look at the Lewis structure of silicon tetrachloride, for instance, it would just simply look like silicon bonded to 4 chlorines. As you can see, there aren't any non-bonding pairs. For those of you who don't know the Lewis structure, I'll put a link to my past AP video in the description. But the derived structure includes the non-bonding pairs. Like ammonia, for instance, has a non-bonding pair, and this has an effect on the molecule's geometry. Both ammonia and boron trifluoride have the basic AX3 formula, but because ammonia has a non-bonding pair here, it makes some more of a bent structure rather than a flat triangle structure. And there's actually a whole lot of these guys. Here's just a few. All of them are derived structures, and it also changes their geometry. And here's the last one. Now the angles here are assuming that lone pairs, in other words non-bonding pairs, take up the same amount of space as a bonding pair. Now here are some shapes drawn. Now, I apologize that I'm not the best 3D drawer, but it should give you a basic idea. So as you can see, water, it has a bent structure like this. So you can imagine these two lone pairs in like this to make a tetrahedron at some point, right? If you connect all of these and all the vertices, then you're going to end up getting a tetrahedron at some point. Ammonia is the same, except it has 3 X atoms, as in the non-central atom. So it only has one non-bonding pair up top. Let me highlight it. So it'll actually behave like an AX4 molecule like carbon tetrachloride, except the fact that because this is a lone pair, its formula will be AX3, but its geometry will be like AX4. I know it's confusing. I know it's understandable, but like the electrons are just kind of a confusing business. However, as you go on, it's gonna get easier and easier with a bit of practice. And to finish off the video, I'll show you some more 3D shapes of the molecules in the derived structure. So here's the AX4E structure, a derived form of AX5. And this one is AX3E2, AX2E3. As you can see, when AX5 is taken and then derived, we get this basic polite structure followed by 3 equatorial atoms or lone pairs. Now if you compare this structure to the original AX5 structure, you'll find that they're honestly pretty similar. However, unlike the AX5 structure, these derived structures all have a lone pair. However, they still follow the AX5 geometry. And these are the 2 derived structures of the AX6 form, where this is AX5E, and this one is AX4E2. Now you may wonder why I'm writing these formulas like this. So, A basically represents the central atom. For iodine pentachloride, for instance, that would be the iodine, since it's the least electronegative atom that's not a hydrogen. X is the non-central atom. For here it's chlorine, and E just means the number of lone pairs. So if it has 1, it would be 1 lone pair, as you can see here. So that was a short video about the VSEPR theory and molecular geometry. Thanks for watching, and see you in the next AP chemistry videos. Bye!